Hello, welcome to all. Myself, Dr. Santhosh Singh, working as an associate professor in Department of Physics, Institute of Aeronautical Engineering. Today, I am going to discuss about neutron cross-section. This topic comes under nuclear materials course structure. So, let's start the topic. So, what is neutron cross-section? Actually, neutron cross-section or nucleus cross-section, it's measure the probability of how neutron and nucleus are any incident particle during nuclear reaction, any incident particle during nucleus reaction which are approaching towards the nucleus, how they are interacting. So that interaction will be measured in terms of cross sections. Okay. So as a classical definition, it is basically the area where these reactions take place. Means around the nucleus, what are the effective area where these reactions will happen, or when neutrons approach towards the nucleus, then what will be the area around the nucleus where neutron will go for nuclear reaction. So that area is known as cross sections. So both neutron cross sections or nucleus cross sections, both are equally same, because neither alone nucleus nor neutron can make reactions. So whatever the possible region, that region is known for both, means for neutron and for nucleus. Okay. So it is clearly written here, the probability that a certain reaction will occur is measured in terms of an area called neutron cross sections or called nucleus cross sections. Means, suppose if any consider nucleus, suppose this is your nucleus which is going for nuclear reaction, and this is an incident particle, suppose it is a neutron. So this neutron, when approaches to this nucleus, so nearby this nucleus, any region that nuclear reactions will happen. Not generally, students think that when neutron strike this nucleus, then only the nuclear reaction will take place. So this is not an exact case. Obviously, neutron can exactly strike with this nucleus. Then that type of reactions is known as a scattering phenomena. But all the major nuclear reaction like nuclear fission or absorption are happen nearby the nucleus, not at an exact nucleus. Okay. So why nearby nucleus? Because this nucleus have some potential nearby it, and that potential is governed by nuclear forces. That forces are very short range forces, but very, very powerful. So nearby the nucleus, where that potential is present, in that potential region, this incident neutron will go for nuclear reaction. So this region is known as a cross section for both neutron and nucleus. Cross section. Why? Because nucleus also go for reaction, and neutron also goes for nuclear reaction in this region. Okay. So what is neutron cross section or what is nucleus cross sections? It is nothing but an effective area where the nuclear reaction will occur or where the nuclear reaction will take place. There are several forms of nuclear reaction, whatever the form, that will happen where that region is called neutron cross sections or nuclear cross section. That is written here. The probability that a certain reaction will occur is measured in terms of area, okay, called the neutron cross sections. So classical definition is an effective area where neutron nucleus will go for interaction or will go for nuclear reaction. And as a quantum mechanical definition, it is a probability where in which region there is a strong probability for nuclear reaction. That region is known as nucleus or neutron cross sections. Here I considered neutron as an incident particle. There are another particle also, or maybe some different particle which will go for nuclear reactions. Then if there is different particle, then you can say cross section for that particle. Okay. So all this thing I want to show by pictorial diagram here. So here one incident thermal neutron approaching towards the nucleus. I put deliberately here the neutron. See this neutron approaching toward the nucleus, not at exact nucleus position. Why? Because around the nucleus there are certain fields where this neutron goes for nuclear reactions. Okay. So when it approach in this region, it will be goes for fission. Okay. When this incident neutron will approach in this region, it is just captured. Captured means absorbed. Okay. So this absorption phenomena will be two types, means simple absorption and again emission, or absorption and some different nuclear particle will emerge. Okay. So that is different thing. Just I am focusing here about neutron cross sections. So when neutron approach in this region, this sky region, then it will be go for scattering, and one another region that is shown here by white color. When incident neutron will approach this region, this incident neutron will go for geometrical scattering, exact collision type of thing happens. Okay. So this white region has exactly same dimension of this considered nucleus. Okay. So you can see the fission area, this fission area is larger than comparison to other considered area. Means other considered area are what? This capture region or this scattering region and this exact geometrical collision region. Okay. So what I am trying to say, this fission region also contained whole region. This fission region is shown by this gray color circle. Okay. So it doesn't mean this blue is out of from this gray region. No. I am talking about, that's why gave the definition in quantum mechanical term. I am talking about the probability. So, by seeing the effective area, you can see what type of reaction will be more probable when neutron and nucleus reaction will take place. Okay, so by seeing the area, you can tell that fission is more probable than any other type of nuclear reaction like capture, scattering, and geometrical collision type of thing. So you know the dimension of nucleus. It is around, radius is around 10 to the power minus 14 centimeter. So if we consider the area around the nucleus, it is also very, very less. And such type of area is represented by in term of Born. Born is a special unit for defining the neutron or nucleus cross section of during the nuclear reaction process. So see the fission area, it is around 583 bonds. Capture region, it is around 99 bonds. Scattering region, it is around 10 bonds. And geometrical region, it is around 1.74 bonds. Means the area, which area is greater? The fission area is more greater than other possible nuclear reaction components. So we can say that fission is more probable because their cross-sectional area is more. Okay. The same thing I want to show here. So this is cross-sectional view of this figure. This figure is cross-sectional view of previous figure. So here I want to show that fission region have more area, more cross-sectional area, so that we can say again if fission is more probable in any kind of nuclear reaction. Also it's depend on targets and approaching particle toward the targets, but generally fission is more probable than any other means capture, scattering, or geometrical type of geometrical collision type of nuclear reactions. Okay. Why? Because fission, where fission can take place, that area is larger than other considered components. So in general, the neutron cross section is an effective area that quantifies the likelihood of certain interaction between incident neutron and target object. Effective area. Already I told. It must be noted that this likelihood does not depend on the real target dimension. Okay. I already told. Here. Your nucleus is here. But these reactions does not depend on this considered target dimensions. Means your reaction, where your reaction will take place, it does not depend on your target dimension, your target nucleus. Okay. So in the vicinity, means in neighborhood of the target nucleus, neutron is subjected to strong nuclear forces of target nucleons. Nucleons, in my previous lecture, I already cleared this. What is nucleon? Nucleons is nuclear particle which present inside the nucleus. So who is present inside the nucleus? Proton and neutron, collectively called nucleons. Why? Because these proton and neutrons are present inside the nucleus. Okay. So the interaction strongly depends on many variables such as a type of target nucleus and neutron energy. So these are the governing factor. Type of target nucleus and neutron energy means whatever the fission, first one. Second, what is absorption? Third one is called scattering. And fourth one is geometrical collision. So which type of nuclear reaction will happen during the neutron nucleus reaction? It depends on the target nucleus. Target nucleus means which type of material is there, means for boron, silicon, carbon, different material have a different approach. So, and what is the energy of incident particle? Here I consider the incident particle as a neutron. So, what is the energy of neutron and what type of target you have chosen? That two things only govern these phenomena, means fission, absorption, scattering or geometrical collision, and also governing where these things happen, means fission can happen from here to here, okay, here. Capture can happen from this region to this region. Scattering can happen only in this region. So where it happen, okay, so means if fission is going to happen, so fission is happen here or here, means how nearer to nucleus it will be going to happen. It all depend on what type of target nucleus and incident neutron energy. It is observed that, means scientists performed many experiments and they observed that radiative capture and fission are much more likely for slow neutron than for fast neutrons. Means radiative capture means absorption. Capture is a similar phenomena like absorption. Radiative capture is a similar phenomena like absorption, but in this radiative capture process, one another form of nuclear particle will emerge. Means suppose this is your considered nucleus, this is your incident neutron. When neutron approach towards nucleus for making a nuclear reaction, then it will be, suppose if it will be absorbed by this nucleus, okay, means the whole entirety of neutron will vanish and one another kind of, suppose for example I am telling, some gamma plus kind of nuclear particle will emerge. So this process is known as radiative capture. Okay, it is similar to an absorption, but here also emission will take place in form of some different particle. Okay, so this is radiative capture. So what I am telling? I am telling radiative capture and fission are much more likely for slow neutron than for fast neutrons. Okay, means this fission process and radiative capture process will be more probable, will be happen frequently for slow moving incident neutron comparison to fast moving neutron. For example, if any incident neutron having approached towards nucleus with velocity v1 and one another neutron which having velocity v2 and approaching towards nucleus, and if v1 is very less than v2, okay, and both are having capacity for going for nuclear reaction, means they are having more energy than threshold energy, but comparison to velocity, both neutron having more energy than threshold energy, but comparison to kinetic energy, if this V1 is very less than V2, then this neutron N1, suppose this is N1, this is N2, this N1 is more probable will goes for radiative capture or fission, okay, than V2, okay. So that's why it is written here, radiative capture and fission are much more likely for slow neutron than for fast neutrons. Second thing, fission is always more probable than radiative capture. So also in comparison between fission and radiative capture, fission is more probable, means there is a chance fission will happen, okay, comparison to radiative capture. Now I explained radiative capture. In my previous lecture, what is fission, I have already explained. If you want to know what is fission, go for my previous video lecture, okay. So again, the next thing is written here, these areas are extremely small, being of the order of 10 to the power minus 22 to 10 to the power minus 24 centimeter square. So you can imagine how small area it is around the nucleus. Means measuring of these area where the nucleus will go for nuclear reaction, it also very critical. That's why a new unit for measuring such type of low area was emerged, and it is known as Barnes, okay, and its range in between 10 to the power minus 22 to 10 to the power minus 24 centimeter square, okay. So these area will be measured in term of bar. And what is bar? 10 to the power minus 22 to 10 to the power minus 24, okay. 1 bar is equal to 10 to the power minus 22 centimeter square, okay. So I just want to request all the viewers or all the students, try to imagine such a small area, okay, around the nucleus, so that you can imagine the difficulty also, how our scientists trying to effort. Why? Because why I am dealing with these nuclear reaction? Because I want to energy, pollutant free energy, nuclear resource, using nuclear resource. I want to draw a pollution free energy by using nuclear resources. So, but how this nuclear energy will emerge? It will be emerged either by through any nuclear process, means either by fission or fusion or for radiative capture process, and that fission, fusion or radiative capture process will happen where? In too much small area nearby the nucleus, too much small area nearby the nucleus, and you have to send your incident neutron or any incident particle nearer to that region, then only it will be go for nuclear process, okay. Generally, for making too much effort, even any one try to shoot any particular point, they are unable, after practicing, they are unable to shoot that point. But imagine such a small region, you have to send such a small particle there. So how precise thing you have to measure, okay. So that's why this theory will become important, means this notion of this nuclear material concept will become important. Okay. So further, this cross section will further classified as a fission cross section, absorption cross section, radiative capture cross section, inelastic scattering cross section, and elastic scattering cross sections. Means all are cross section. Here I told that all are cross sections. Here this is a fission cross section. This is for capture cross sections. This is for scattering region. This is a scattering region. So if you measure this region in term of Born, this is known as a scattering cross section. Okay. And this is for geometrical collision cross section. If you measure this region, this dark red region, then it is what? This is geometrical collision cross section. So cross section is a overall term. When we further classified this cross section in their specialty, means if neutron will goes for fission, then it is fission cross section. If it will be goes for capture or absorption, it is a capture cross section. If it will be go for scattering, then it is scattering cross sections. And if it will be go for direct geometrical collision, then it is geometrical cross sections. Okay. So this absorption or capture cross section is two type. Further, this absorption cross section is two type. Absorption cross section means simply neutron will absorb by nucleus, and or it will be first absorb and then it will be emit as a some different form, means some different type of nucleus, nuclear particle, some different type of nuclear particle. Okay. And further, that scattering cross section is also defined as a inelastic scattering cross section and elastic scattering cross section. Elastic means neutron approach, reach that region. Suppose this is elastic region. This is your incident neutron. They approach this region and bounce back. If they bounce back with same velocity, then it is a type of elastic scattering. And if during the scattering bounce back or scattered, also scattered, simply this is your neutron which will go for nucleus reaction. This is your consider nucleus. Okay. So this is your incident neutron which is approaching towards the nucleus with velocity v1. Okay. Now, if it will approach in this scattering region, this is your nucleus, and vicinity of this nucleus, there is a one scattering region or scattering cross section. So when your considered neutron will reach in scattering region, then there is a possibility that they will scatter from this region. Means they will move towards this direction or this direction or this direction. Means scattered. And during this scattering process, if this incident electron will not lose their energy, then it is a elastic scattering. And if it will lose their energy, then it is inelastic scattering. Okay. So if there is no change in their velocity or kinetic energy or any kind of energy, then it is elastic. And if they change their energy, then it is inelastic. Further, So sum of these sum of all kind of cross section is known as a macroscopic cross sections. Means fission, absorption, radiative, capture, inelastic, elastic, whatever this microscopic cross sections area, if you sum up all, that is known as macroscopic cross section, and it will come under equivalent area. Okay, so that thing is defined here. So suppose in previous example I am considered a single nucleus. I gave the example of single nucleus for normalized all the thing, means it is easy to understand when I took example of single nucleus. But it is not possible to take a single nucleus as an entity. You have to choose some part of the material, means 1 mole or some milligram of material, and some milligram of material also contain millions of atoms, and then obviously also millions of nucleus. Okay, and each nucleus have their own cross sections. So that thing is written here. The macroscopic cross section is denoted by sigma, which is corresponds to the total equivalent area of all target particles per unit volume. Means per unit volume, how many atoms is there, and for every particular atom there is a total cross sections. Okay, so if we considered whole entity for per unit volume, means per unit volume, suppose 10 atoms there, means 10 nucleus. So considering all 10 nucleus, what should be the sum of all 10 atoms total cross sections? Okay, so it is denoted by sigma. So if n is the atomic density of considered target material, so what is the macroscopic cross section? Macroscopic cross section sigma is equal to n summation is equal to, this is actually summation, sometimes sigma also told, but sigma is also here written. So we summation is equal to n multiplied by sigma. Sigma, what is sigma? Sigma is your total cross sections for one nucleus. Okay, so per unit volume there are n nucleus, so total cross section is what? N multiplied by sigma, and that thing is denoted by summation. Okay, so where n is the atomic density of target and all, so it is very easy, it is not very difficult. Therefore, since the cross section can be expressed, cross section, nucleus or neutron cross section can be expressed in terms of Born, which is equivalent to 10 to the power minus 22 centimeter square. Okay, and the density is represent in term of centimeter per centimeter cube. Okay, so unit of this summation is what? It is centimeter inverse. Okay, so centimeter inverse means how neutron will travels per centimeter inside the nucleus, inside the material. Okay, that is also a very important term. Microscopic cross sections means what? How much your incident particle will go or will travel inside the considered target. Generally, if you think, if you imagine, it is about how when sigma involved, means cross section involved, it is the area where probability or chances for nucleus reactions. So when that neutron will reach that type of area where it started, incident neutron will reach in that region where such type of nucleus reaction will probable, means chance or probability of happening of a nucleus reaction is high, and in that region how much that travels a distance. Okay, so this is very important thing. Means in that region nucleus incident neutron definitely will vanish. Okay, either it will be absorbed or going for fission. Okay, so in that region how much, means where the chances is very high for nucleus reaction. Suppose I am going to give one example by pictorial diagram. Suppose this is the region where all nucleus cross section is there. Okay, and neutron cross section is there, and your incident neutron is reached here. Then after entering in this region, definitely it will be go for some nuclear reaction, and definitely. So, but how much distance it traveled inside that probable region where nucleus reaction can happen, that thing is measured by macroscopic cross sections. Okay, so this is also very important quantity. Now absorption cross sections. So if the neutron is absorbed when approaching the nuclei or nucleus, so the atomic nucleus absorption, I am talking about absorption cross section. So if any incident neutron approach towards the nucleus, consider nucleus, then there is a chance it will be go for absorption. So this is your absorption cross sections. So what happened during the absorption? So if neutron absorbed, what happened? The atomic nucleus, this nucleus moves on the table of isotopes by one position. For instance, suppose if this is the case of uranium-235, it will become uranium-236. Why? Because this nucleus absorbed one additional neutron, and this star is indicating the nucleus is in higher energy state. Okay, now what happened? This nucleus will remain very short of time, will remain in same state very short period of time, and they will decay this neutron. So they will decay this neutron as a different particle or same as a neutron also. So this energy has to be released, and release can take place through any of several mechanism. Means how that neutron will decay, or that nucleus will go for their stable state. The simplest way for the release to occur is for the neutron to be ejected by the nucleus. Means whatever he absorbed, whatever the nucleus absorbed, the same thing they ejected. That is the very simplest process. Okay, and what is the next thing? If the neutron is emitted immediately, it acts the same as the other scattering events. Then that ejected neutron will be go for other nucleus process. Okay, further. Now what is the second thing? The second thing will be the nucleus may emit gamma radiation. Means that neutron is permanently absorbed by that nucleus, and for getting the stable state. Why? Because when it absorbs the neutron, it is in higher energy state. So for getting the new stable energy state, it will be emerge some other kind of radiation that is known as gamma radiation. Either it will be go for beta decay, means beta particle, they will emerge. Okay, so about it is observed that 80 to 82%, 81% of isotope uranium-236, means higher energy state uranium-236 nuclei are so energized that they undergo for fission, okay, releasing the energy as a kinetic motion of fission fragment. Means another chance is what? It will be go for fission, means breaking of itself, fission. Nucleus will collapse in a two part or whatever. I already told in previous lecture what is fission. Fission means one big nuclei will be separated in two smaller nuclei. So this is three process. Four process means either it will be, first one is what? It will be emerged same as a neutron. Second one is this absorbed neutron. Nucleus will, after absorbing the incident neutron, nucleus will emerge a gamma particle, okay, or beta particle, or go for fission, okay. So here I am going to discuss about fission cross section. So fission is what? Fission means one bigger nuclei will decompose into two or more than two smaller nuclei, break into two smaller nuclei. So that is different thing. What I am want to tell here, see here the one graph is plotted between energy and fission cross sections. Okay, fission cross section of uranium-235. So see, fission cross section means probable area where fission will be happen or maybe happen is more for when the incident energy, neutron energy is low, and when energy become high, the fission cross section means the chances of fission become low. Okay, so this thing already I told means the fission is more probable for slow moving neutron or slow moving incident particle. But incident particle velocity is if too high, then there is a less chances for fission. So fission is a very important for getting a nuclear energy. Okay, fission is one of the most important process for getting the nuclear energy. So we should also take care of our incident neutron or any incident particle energy, so that they can also cross the barrier, means able to penetrate inside the cross-sectional region where different kind of nucleus reaction will take place. And for getting the fission process, we have to become a selective so that fission will take place. Okay. So this is the same thing all the written here. For a given target and reaction, the cross section is strongly dependent on the neutron speed. In the extreme case, the cross section can be at low energy, either zero. Okay. Such physical constant explain why most operational nuclear reactor use a neutron moderator to reduce the energy of neutron and thus increase the probability of fission. So the concept of moderator is used in nuclear reactors. So that moderator will reduce the energy of incident neutron, so that fission will take place. Okay. Now reaction rate. Reaction rate means how many incident neutron will goes for nucleus reaction. Okay. So suppose this is your sigma, means cross sectional area, total cross sectional area, and there are several incident neutrons approaching this cross sectional area. Okay. They are having velocity v. So in dt time, how many in dt time, the distance traveled by this incident neutron is what? V dt. Okay. So consider this spherical volume, which length is V dt. Okay. And this base area is sigma. So what is the formula of cylinder? Cylindrical shape, any cylindrical shape, what is the formula? Base area pi r square into h. So here area is what? Sigma, and height is what? V dt. Okay. So this hypothetical cylindrical volume, the neutron, all the neutrons which contains inside this hypothetical considered volume will be goes for reaction. Okay. The same thing is written here. So volume is what? Sigma v dt. If density of incident particle is n, then the total number of incident particle present in volume v is what? N sigma v dt. Okay. Suppose density of incident neutron is n. So total number of neutrons which is inside the considered spherical volume is what? N sigma v dt. So if r is reaction rate, so what is reaction rate? Reaction occur per second. Okay. Means nucleus reaction will take place in 1 second. So number of incident particle per second on the target it was, if we divide by dt, then this is n sigma b. This is your reaction rate. Okay. So I think this is enough for today's video lecture. I will cover some other nuclear material topic on my next video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.